Okay, good morning, everyone. My name's Aaron Pearlman, for those who don't know me. I'm a postdoctoral fellow at McGill. I'll be your chair for this morning, so welcome, everyone. So day 2 of the FRB workshop here, we'll be talking more about how to use FRB localizations to get more information about FRBs. And we have 2 great talks prepared for you this morning. First up is Clancy James. And we'll have a discussion section after the first 2 talks. So Clancy, the stage is all yours.
Okay, thank you very much, Aaron. I did a mic test earlier. Hopefully everyone can hear me. So I'll be talking about the distance measures and how these can be used to affect our understanding of the FRB population. It's curious to note that I'm in Perth, Australia, which is close to this purple marker here, which is almost at the antipode of Toronto. So I'm not quite the opposite side of the world, but I'm almost as close as you can get while still being on land. So before I begin, I'd like to pay my respects to the Whadjuk people, the Noongar Nation, and they're the traditional owners of the land in which I'm sitting on right now, and also the Whadjuk Yamaji people as the traditional owners of the Murchison Radio Astronomy Observatory, which is now known as Inyari Manya Ilgari Bundara, or Sharing the Stars and Sky, which is where ASCAP is located. But also, thank you very much to the organizers, and I guess by that I mean Ziggy et al., for the remote presentation. So various traditional owners around the world recognize that climate change means the destruction of the traditional way of life. And so if we pay respects to them, we should be keeping track of the impact that astronomers do have, especially through things like supercomputing travel. And so we've got a responsibility to reduce our carbon footprint. But remote presentations are also more inclusive, for instance, to people with kids. So thank you very much. So with that underway, and that was just an excuse to show my cute daughter in case you didn't get that, let's talk about redshift and dispersion measure. So the Makar relation, probably everybody can close their eyes and sketch this plot exactly. It's been shown so many times. I think the paper's up to about 300 citations now. So what is it? 30% of the Lorimer burst. We have redshift on the x-axis and dispersion measure, or the cosmic contribution thereto, on the y-axis. And when this analysis was done, there were 5 fast radio bursts from ASCAP analyzed, and these 5 colorful points, and some gray and therefore obviously less important ones by other instruments. The point was to have a controlled sample. And we see that as redshift increases, dispersion measure increases. And you can draw a lovely black line through the center of that. And that black line is the mean ionized density of the universe, which is essentially the baryonic density of the universe multiplied by the fraction of those baryons that are in diffuse gas, multiplied by the fraction of electrons in that gas that have been ionized, and cosmological factors. So it's also worth pointing out here that it's great that this is now known as the Makar relation in honor of JP, who is my former boss here at Curtin University. But also, this idea of using the dispersion measure of extragalactic bursts to probe the baryons was really proposed by Ginzburg back in 1973, and then Ioka and Inoue in the context of GRBs later on. So, okay, beautiful relation, but if you just take this and then you turn it on its side, which is very easy to do in PowerPoint and less easy to do in paper, where you plot the DM on the x-axis and the redshift on the y-axis, which is essentially saying, okay, you see an FRB with a measured DM, right? What's its redshift? This is what you do with follow-up observations. You will see that this is absolutely not a one-to-one correlation, right? Here we have 3 fast radio bursts with similar extragalactic dispersion measures and a factor of 3 difference in DM. So whilst it's clear that, the universe has some mean density, there's a lot more going on. And obviously the best example of this was by FAST and the resulting localization in New et al. Of FRB 1905-20b with this huge DM excess out here, right? So the importance of localization is to say, really, we can't use this one-to-one, we can't use the Makar relation, or at least we can only do so very broadly. A lot of modeling papers will use a one-to-one ZDM relation because it's easy, right? QIIME have a beautiful sample of dispersion measures. It would be lovely to interpret them directly as distances. But I think the most that I can say about this while sticking to the rules of etiquette in academia is to ask the authors who do so to please kindly stop doing this, and I'll say no more. So what's this joint redshift dispersion measure distribution? So if you're a theorist, you probably think about it like this, right? We can expand P of Z dm into P of dm given Z and P of Z. Can I quickly ask, can you see my mouse, by the way, when I move it around, the cursor? Yes, great. Thank you for the thumbs up. So if you're a cosmologist, this term here, P of dm given Z, represents the structure of the universe, right? Whether or not it's the halos or filaments or just host galaxies, right? Whereas this P of Z is the FRB population. So you've got this distribution of probes that are going off at some redshift Z, and they're probing the structure of the universe by P of dm given that redshift. However, let's supposing you're interested in FRB follow-ups, and I'm assuming that's the perspective some people in the audience are coming from. You probably think about it like this, right? You have a radio instrument measures a dispersion measure. I think QIIME have a lovely paper and FRB sent me a DM, right? That's what they do. And then you do a follow-up and you have the redshift for that FRB, right? P of Z given DM. So if you want to try to understand this, you need to include a lot of things. You've got your cosmology, right? Hubble constant, feedback, or whatever we choose to call it. Fluctuations, perhaps. Baryonic density. You've got whatever FRB host galaxies are doing. You've got the FRB spectral luminosity and source evolution. And then you've got the biases in your instruments and you match predictions to observations. So just to give some slight historical perspective to this, Caleb et al., Manisha's paper here, was probably the first to give what you'd say is a good forward model of fast radio bursts, right? Where you start by putting them somewhere in the universe and seeing what happens when they arrive at Earth. And now FRB Poppy is really state of the art, right, in doing forward models. But as Liam Connor will tell you in a paper here, what you really need to do is take such a forward model, then vary the various parameters of that model, fit that to your observations, and then make decisions about which model is more or less correct based on that. So Ray Lau et al. Were probably the first to do this. I've jumped into this game, and basically I started doing this because of various arguments with JP about systematics in the Makar relation paper. So I said, right, if I can't convince you to do that, then I'll do it myself. And then QIIME have done this with Caitlin's paper, Shin et al. So when we model, do this modeling for localized ASCAP fast radio bursts, this is what we get. So the background shading here, and it's a log scale, gives you the probability that the model says you will detect an FRB in this ZDM space, right? The dots are measurements of localized fast radio bursts with ASCAP. This is taken from, I should have put a cited myself here, but anyway, this is the sample up to the end of 2021 being shown here. And these lines are FRBs for which we don't have a localization. We've got the dispersion measure, but we don't have a redshift. So that's the kind of modeling you do. So I'd like to expand a little bit more briefly on what X was talking about yesterday about the role of feedback and the Hubble constant, just to illustrate this. So as X explained, because the feedback keeps the cosmic gas puffed out. So if you have a low amount of feedback, then you can have the gas condense onto halos. You get very large fluctuations in the universe, and then the DM, due to the intergalactic medium, is very spread out. But if there's high feedback, the gas can't condense, and you get it all coalescing around the Makar relation line. Now, why exactly do we find this horrible degeneracy with H0? So the main constraint on the Hubble constant is the minimum density of voids, right? So the slope there is basically proportional to H0, right? The dispersion measure has a constant H0, assuming you keep omega B fixed. Now you can vary that slope, right? And if you imagine the bottom part of that slope is this yellow line here, well, clearly all your data points still fit that, right? They're above the line. But as soon as you put the line like that, then you clearly have violations where you would have this FRB here and this one there having too little DM, and they've gone through some anti-DM matter, which of course doesn't exist. So that's why you get this sort of asymmetric constraint on H0, where you can have higher values tend to be allowed, but a sharper cutoff at the low value. Now, okay, so that's how H0 works. Now, if we compare that to the feedback scenarios, this is for the same value of H0, but with a low amount of feedback. This is the slope of that minimum DM line. And with high feedback, this is the slope. And so this is the effect which causes this degeneracy. And so that's why Jay has been finding that there's a large amount of degeneracy between these two parameters. Okay, so that when we saw this, this was our working title for the paper, which stayed as a working title. Anyway, okay, something else to mention is that when you're doing this modeling, let's imagine you're asking, okay, we've discovered a dispersion measure. What's the probability of some particular redshift? Well, the two answers you can give are one, well, you get some probability distribution due to the intrinsic variation in your model of cosmology, but you've also got the uncertainty in that model. So for instance, we had this lovely model of the ZDM distribution that I pointed out, and then my lovely colleagues in craft discover this FRB out here and localize it to a redshift about above 0.01. And this outer contour here is the 99% contour. And so it sits outside of that. And you can imagine I was a little bit worried about this, but obviously this distribution is only for the best fit parameters. Now, if you then say, okay, here's redshift and here's the probability, well, the cumulative distribution for the probability of redshift given the dispersion measure of this FRB. Well, given this best fit model, you get this solid blue line, and you would see that a redshift of 1 is very unlikely given that best fit. However, if you include the 90% statistical variation limit when fitting that model, you get this large gray range, and quite clearly it's consistent with that. So it's difficult to show this full range of uncertainties because for every point in this multi-dimensional space, you produce a new plot like this. But if we take our new value of Emax, right, we increase Emax within its 90% confidence level, which produces this cumulative distribution there, then we get this new ZDM plot, which was consistent with the old measurements at about 1.6 sigma, and it's quite accommodating. So, okay, that's probably enough about ZDM itself. Let's use it for fun and profit. So one thing we can study is the FRB luminosity function. So as has been mentioned, it tends to get fit with this Schechter function, and it gets fit with a Schechter function because people love power laws, and it's basically a power law. This is technically an upper incomplete gamma function, but people also don't like sharp cutoffs. So we put in this nice exponential decrease to make things smooth and happy. And I want to point out that when in my paper, which fits these parameters based on ASCAP data and a little bit of Parkes at 1.4 gigahertz, and we have Chime data, which is 400 to 800 megahertz, completely different instrument, independent analysis by Caitlin Shin, we get quite consistent values for the cumulative slope of the luminosity. Oh, maybe that's a differential slope. That's cumulative slope of the luminosity function and the maximum energy, right? So I think that actually says that we're doing reasonably here, right? When you get these independent fits and get consistent answers. The other thing to point out is that this was mostly done with localized FRBs, and this was done with about 30 times as many unlocalized FRBs. And purely the statistical uncertainty is much larger with the unlocalized sample. Now, okay, so that's just a functional form that seems nice, but with enough FRB localizations, we can just measure this, right? You can just measure it. One of the problems here is that progenitor models are probably not sufficiently predictive to give us a form for this. And what we can do though, is say that, we know that pulsar giant pulses exist, and maybe they extrapolate to FRBs. So with this paper by Aperba et al., where they measure the rate of giant pulses from the crab, they get this differential power law index of minus 1.81, which is not consistent with what we see with FRBs. So, okay, clearly many orders of magnitude difference in luminosity, but it is interesting, right? Whereas if these numbers were identical, it would be very suspicious. Also, we can compare this to known FRB repeaters, right? So these measurements of 121102 by FAST, by D. Lee et al., show this rather complicated structure for the luminosity function. And you could say, okay, how about we compare this functional form to these objects, right? So I don't think at the moment measuring the luminosity function is sufficiently useful for the microphysics of the emission mechanism, simply because the progenitor models are not predictive enough, but clearly it has value in comparing to observational properties, even if we don't necessarily understand the physics behind these. A little bit of a side, I don't know if anyone from FAST is in the audience, but this is a workshop, so let's generate discussion. And the best way to generate discussion is with controversy. So let's start something now, and I'm safe the other side of the world in case things get nasty. So we know that the notion of completeness, right, is a function of fast radio burst width, right? So if you treat it in constant fluence, wider things are harder to detect, and in constant luminosity, thinner things are harder to detect. So that means that whenever you say you've got a telescope threshold, it's a soft threshold, right? You can't define a very clear detection threshold in either fluence or luminosity space. So there was this interesting paper by Zhang et al. And Zhang et al. In RAA, it's on the archive, that showed that for these three well-studied repeaters for which FAST has very good measurements of the luminosity distribution, and they're localized, we have quite different this is the FAST threshold relative to their measured spectra in terms of energy. But if you write this in terms of fluence, you find that their downturns all happen at a very similar fluence just above the FAST detection threshold. So my suggestion is that this is due to completeness of the FAST threshold, because it seems coincidental to me that these three repeaters all choose to have their downturns at an energy that corresponds to the fluence as would be measured here on Earth. So my challenge is to prove that this is not a selection effect. Okay, that's the bit of controversy aside, let's move on. So the other thing that you can measure is the evolution of the FRB population. You can ask, maybe FRBs come from young magnetars. If so, they should closely track star formation, right? The delay time between forming a young magnetar from a massive star going supernova is effectively identical to star formation on a cosmological scale, right? Whereas if it comes from, let's say, a binary merger scenario, then it'll be subject to a delay time distribution. And I will also point out that these things get quite complicated. If you look up the modeling papers for delay time distributions, there's a lot of details there. So the current naive model that tends to be used is to simply scale this with the star formation rate. So you take the star formation rate, McDowell and Dickinson, for instance, you normalize it to the star formation rate in the local universe, and then you just assume that the FRB population evolves with this rate to some power of n, right? And then you need to account for the time dilation factor because it's a rate. So this was introduced by JP and Ron, Makar and Eckers here, with the idea of saying, okay, if n is 0, it's about long delay times. N is 2, that's very peaky. That's like AGN, and n is 1 is star formation. Ron absolutely hates this modeling, by the way, so I love attributing this to him in a public audience. He'll listen to this at some point. Okay, and when you do fits to this, again, myself, my sort of results with others and Caitlin's results, we get something fairly consistent with the star formation rate, right? N is 1 is star formation rate. So about 1 plus or minus 0.5, about 1 plus or minus 0.6 or 0.8. So you can say that the fits are consistent with evolution with the star formation rate, but fits of the form 1 plus z to the n are equally good, right? So if you look at the star formation rate here, yep, it increases as you go back in time, but then you have this typical turnover around redshift 2, and then the star formation rate plummets at higher redshifts. Now, current FRBs that are localized do not probe that, right? We have FRBs at a redshift of 1 that have been localized, and while Chime and others do have FRBs with a DM of around 3000 that could plausibly come from a redshift of 3, they could also be much more local objects that sit in the middle of a massive galaxy cluster, right? So to really probing this, we need localized FRBs at a redshift greater than 2, and that's probably going to require significant JWST time. So if anybody serves on the tuck of that, can I please buy you a drink? All right, so what else can we do with localized FRBs here? So we've been talking about sort of DM cosmic or DM IGM, right? The cosmological contribution to IGM. So we had this discussion yesterday that the current model really looks at the dominant fluctuations are due to the dark matter halos and their occupancy in baryons, right? So this is based on a model from Matthew McQuinn. So you populate the universe with dark matter halos, you fill them with baryons, and you send FRBs through them and work out the total fluctuations. Whereas this one here is sort of skimming the halos, and this one here is going right through a couple of them, and we'll have a large excess. However, dark matter halos are galaxies, and optical observations can identify these. So this was sort of done first in Prochaska et al., where we had FRB, now I guess it's called 2018-11-12A, and it originates in this galaxy, but passes through the halo of this massive foreground galaxy. And so if you estimate your DM budget, you see, okay, it can rise from, we've got the ISM, the halo, the cosmic contribution, and then there's this estimated excess of order 100 parsecs per centimeter cubed from the halo of this galaxy. So the idea behind FlimFlam, which KG Lee is leading, is to identify the intervening halos of, well, all the galaxies along the line of sight. Now, that's great, it's wonderful. The problem is when you want to incorporate that data, we need to take these models of DM cosmic, and then if we're accounting explicitly for the halos, we now need to remove the halo contribution from our DM cosmic estimates and compare to that. However, if what you really care about is the FRB progenitors, then that's fine. You just want to subtract as much of this variation as possible to estimate the DM host contribution. Okay, so this is how I see this working in future, right? This is how I think it's going to play out. Step one, we're going to get lots of nearby FRBs, right? We're going to just measure the luminosity function. We're going to find 1,000 localized FRBs, or 1,000, let's say, at a redshift of 0.1, and they're all going to be at exactly 0.1 because it's just simpler that way. So let's imagine that. And you just look at the luminosity distribution of those things, and wham, you've got the luminosity function. Great. Step two, you find lots of FRBs in the nearby universe, well, redshift less than 1 universe, right? This is still going to be difficult, even with far future instruments, to get many FRBs at a redshift of 2 or 3, but we'll definitely get heaps at redshifts less than 1, where we can identify hosts via 8-meter class telescope observations. And we're going to just measure the volumetric density, right? We know the luminosity function, therefore we can correct for the luminosity function. We just measure the volumetric density. We don't need to put in parametric models. So one thing we should be able to ask, and we need to do more work here, is to think, how many FRBs are we going to need to distinguish a null hypothesis of that all come from young magnetars versus an alternative where, say, 1% are from binary neutron star mergers, right? That's something we should get an estimate for. I haven't done that yet. My guess is at least 10,000 localized FRBs, but we should estimate it. Now, the other complicating factor in all this, in this beautiful scenario I've set out, is the frequency dependence of FRBs. So if FRBs are broad spectrum sources, and we heard yesterday that we're getting joint detections from sort of 400 megahertz up to the gigahertz range between chime and DSA, insert integer number here. So clearly FRBs can be quite broad spectrum. Then you can think of them as needing a K correction, right? To scale their fluence to luminosity. However, if some FRBs are definitely narrowband, in which case you want to describe them as having a frequency dependent rate, right? So rate proportional to some frequency to the power alpha. But whatever your model for FRB behavior, there is some degeneracy between the volumetric distribution and the frequency dependent behavior. And at the moment, our estimates for this parameter, this scaling parameter alpha, are fairly broad, right? This is of order 1 sigma error bars. And this is just an example from an older analysis showing the degeneracy between the n, right, the star formation rate scaling parameter n, and this value of alpha. And you see, yeah, it's quite degenerate. That's not the latest plot. It's better now, but it's what I could find preparing this talk. So ways out of this, well, you can model this, right, just not very well. But you can then use multiple experiments at different frequencies, but then you deal with different systematics. Or you can model the frequency behavior within an experiment, but that's also tough. So that's going to be a bit of a challenge understanding the frequency behavior of FRBs in the future. And it will limit, if we don't understand it, our ability to interpret measured redshifts. Okay, so part 3, biases and systematics. Can someone maybe yell at me how much time I have left? Maybe I've got no time left. I started a bit late, I think.
Yeah, you're running a little long.
Okay, I am going to go quickly through this. And then I'm going to have to skip the part about chime repetition. So sorry. So there's a publishing bias here, right? People are interested in publishing interesting FRBs first, that we did with 220610A. Boring localized FRBs are left to rot. And in the near future, maybe there's a follow-up bias, right? So you only use this for interesting FRBs. So you can deal with this by following up everything, but it won't be the case possible for too long. You can do it by randomly sampling, just 1 in every 10. You can use it by using the statistic P of Z given DM only. So you make some arbitrarily biased cut on DM and you just use P of Z given DM, which reduces your statistics. Or maybe you can make a slice on parameter space. But I think as a community, this is something we should take quite seriously, how we're going to do this. There's a host galaxy bias, because small distant hosts are difficult to detect. So if we take some of the near universe localized FRBs and their hosts and we move them to higher redshifts along here, they very quickly fall below a VLT 10 sigma limit and eventually will fall below even an HST limit. So we'll need to deal with that. Dealing with that is essentially either, well, I'm out of time, so I'm going to skip over the ways of dealing with that. But I want to point out that when we're going to have to use, as mentioned yesterday by Xavier, that we need to include the path probabilistic host association to give a weighting factor for some hosts, right? We might be able to say, okay, here's a localization. I'll use 1905-23 by DSA here. We might not be sure if it's this galaxy, or that galaxy, but depending upon which priors we put in, we might have a 70% likelihood or a 30% likelihood of each one being the host. However, these priors that we use here should be a function of the very model that the host galaxy redshift is being put into. So eventually we're going to have to incorporate this into one big theme. So I do not sadly have time to talk about repeating FRBs and modeling chime here. So I'm going to end it there and go to questions.
Okay, thank you, Clancy. We have time for maybe one quick question from someone in the audience.
Yeah, I have maybe a quick question. There was the paper by Stuart Ryder recently with the FRB detected at a redshift of 1. And they were talking about, maybe you discussed it, but that the maximum energy predicted in your and Caitlin's models was no longer sufficient. So could you just say a little bit more about like your most recent work? Oh yeah, you did discuss it, but.
Yeah. Yeah, so the long and short of it, I probably discussed it and went over it very quickly. The long and short of it was that with the previous best fit maximum energy, this FRB, so this was used the previous best fit plot, this FRB was outside the range, but then if you allow the 90% range of the previous best fit Emax, then it becomes quite consistent. So we did revise up our maximum energy, but I will caution that there are a couple of FRBs that we detected between this sample in red and this new one. And publishing this redshift greater than 1 FRB is a perfect example of this publishing bias, where we threw it out there because it was interesting and therefore extreme, while we left out a few FRBs that are otherwise boring. Although, isn't it lovely we exist in a universe now where we can say, oh, we've got 3 or 4 localized FRBs, but they're too boring to be bothered writing up in a paper. Will, Ryan, can you do it at some point?
Okay, let's thank the speaker again. Okay, so our next talk will be Alexandra Mannings. She'll be telling us about how to study FRBs and their local environments and what we will learn from doing so.
Okay. Hello, I'm Alexandra Mannings. I'm a 4th year grad student at UC Santa Cruz. And the question I was tasked with answering was, how will the locations in host galaxies help solve the mystery of FRBs? That's a very big question, and I'm going to rephrase it a bit as 2 questions. What unique information do we get from studying FRB locations in hosts, and how does this support progenitor studies? So I guess with FRBs, there are different points of exploration. One is probes, much of which we heard about yesterday and also in Clancy's talk just before this, looking at H0, F, mapping the intergalactic medium or studying magnetic fields throughout the universe. And then also thinking about the progenitors of FRBs. So what's necessary to create this phenomenon, and how can we disentangle possible progenitors through understanding their hosts and their locations within them. So I'm going to focus in on the progenitors and the mystery of that. What is creating an FRB? So we can maybe assume that in order to get the energetics and the time scale of an FRB pulse, we might require magnetism and something that is very compact. How do we get that? Seems like there might be multiple ways. Is it a cataclysmic event? Is it something really old, a younger thing? What is the mass? And various scenarios can meet these criteria of creating something compact and magnetized in some shape or form. And so a way to disentangle that is to study the host galaxy and the local environment of the FRB. So again, restating our new questions, what unique information do we get from studying FRB locations in hosts, and how does this support progenitor studies? And I want to go about this by contextualizing unique. What does unique information mean? And I'll do that by kind of zooming in. So starting on the really, really large scales, and I'm going to focus in a bit on this particular FRB 2019-0608b. Looking at the really, really large scales over cosmic scales, then zooming in a bit, looking at the host galaxy scales, and then zooming in a bit more and looking at the specific FRB location in the host. So let's start real big. So on this scale, you can use FRBs as probes and get information on the largest scales of the universe, on cosmic scales. So this figure from Simha et al. 2020 shows this really beautiful map that they created of the intergalactic medium along the line of sight of this FRB 1906-08, looking at different views along the side and top view. Through this, you can understand DM cosmic, so the contribution to the DM due to the intergalactic medium and halos that the sightline intersected. And then also as a nuisance parameter, you have DM host. So you can learn a little bit about or constrain the dispersion measure due to the host of the FRB. Among many other things that you could do on this scale, but I think we've heard about a lot of that. So I'm gonna move on and zoom in a little to the host galaxy properties and this medium scale that I am defining. So in Alexa's paper, Gordon et al. 2023, they do modeling of the star formation histories of the all of the hosts in this sample. I'm showing just a fraction of those, so 8 of them, and the one circled there is 1906-08b. These two on the top, what is that to you left, are like rising star formation histories, and then the others are falling in various ways. And 2019-06-08 is modeled as a starburst galaxy. So this recent epoch of very high star formation. This can give us information about the stellar populations that are in these hosts, and what kinds of stars these FRBs might be related to. We can also look at differences between repeaters and non-repeaters. So these are histograms of various galactic properties like star formation rate, specific star formation rate, stellar mass, I'm gonna name them all, metallicity, age, and then like dust extinction. Repeaters are shown in blue, non-repeaters are shown in the pinkish purple color. And they found like no very statistically significant differences between the repeating and non-repeating populations in the sample. There are maybe hints of something with metallicity and mass where the repeaters were occurring in hosts with slightly lower metallicities and masses. But again, that was not statistically significant. But I do think it's a bit interesting just thinking about the possible connection between FRBs and long duration gamma ray bursts, like what people were thinking for 121102 and some of the other repeaters. So that will be interesting to see as we get larger and larger sample sizes. Do they start to separate themselves, or are these overlaps really the case? You can also classify the hosts relative to other galaxies and field galaxies. So this plot from Ivic et al. 2023, Adeze, a grad student at the University of Toronto, studying these 3 repeating chime FRB hosts, which they used path to associate to their hosts. So I guess in this, I also want to say that you don't have to necessarily have a sub-arc-second localization to associate a host or an FRB to its host. Path is very powerful in allowing you to make these associations with larger localizations. And this plot is just looking at the like source of ionization in the galaxies, and we're classifying these hosts in that way, finding that there was a lot of ionization due to star formation, and then one looking like it's reaching the Aegean region there. And then to our specific host that I wanted to focus on, looking at this plot from Bandari et al. 2022 that looks at the colors and then the mass and star formation rates of the hosts in this sample. The one that is circled in the blue circle is 1906-08. And it looks like it's kind of moving into that green valley, and then same in the star forming main sequence. It's kind of a bit lower than that star forming cloud. And I think that this kind of agrees well or goes along nicely with the story that was told by the star formation history in Alexa's paper, where there is this ongoing star formation, but maybe it is, declining. So that's very exciting how these different papers are kind of approaching the same problem in different ways. You can also make direct comparisons between hosts of different transient populations. This paper, Bochenek et al. 2021, found that there was some overlap between the hosts of FRBs and core collapse supernovae, looking at stellar mass, star formation rate, and specific star formation rate. They also compared with long duration gamma ray bursts and superluminous supernovae. And then we can also take more lessons from other communities. This is a plot from Dodd et al. 2021 that looked at the host characteristics of changing look AGN. They found that most of the changing look AGN in their sample, these blue squares that are showing up, were landing in this in the green valley. So kind of transitioning to turning off their star formation. And in their paper, they also talked about the relative shapes of the galaxies, whether they were undergoing major or minor mergers, and how these different quenching processes were kind of invoked in the turning off and on of these changing look AGN. So lots of information that you can get from looking at the global properties of hosts of various transients. You can also study the magnetic fields in the FRB host galaxies. Paper from, not a paper, a figure from Mannings et al. 2023. This is a plot showing a PDF from simulated sight lines using the Auriga cosmological doom simulations, MHD simulations. The purple is a PDF of the rotation measures. The pink is a PDF of the dispersion measures. And then the vertical lines are the observed values. And here we're characterizing the host magnetic field. They're in relatively good agreement, but we can see that there's a bit of excess RM and a bit of excess DM in the observed values for the rotation and dispersion measures, which I think can tell us also a bit about the progenitor environment. So if there is a bit of that excess rotation measure, what's happening kind of immediately around the burst itself, but then also we can say something about the global properties as well. So there's a lot we can do on this scale on individual basis and also these large statistical samples. So now I'm going to zoom in even more. And now we're going to, I guess, what I was supposed to be talking about now, the unique information that we can get from locations in their hosts. Warning, the next few slides contain shameless plugs and pleas for precise localizations and high resolution imaging. So first off, in Mannings 2021, Mannings et al. 2021, we found that many of the FRBs in this sample were found on or near spiral arms in their hosts. If they exhibited spiral structure, the FRBs were very close to or on top of them, which I think gives us a lot of hints about what possible objects, the age of the objects, and everything that could be responsible for producing the FRBs. As Clancy was saying, depending on what we expect, we might expect the FRBs to trace star formation or not, and this can give us a hint as to whether or not that's true. In Titidi et al. 2021, they do some really nice modeling of the kind of dynamics of the galaxy, and they look at the position of the FRB relative to star formation and spiral structure in its host. And they find that there was a slight drift from a region of active star formation, but it was still relatively close to kind of like the leading edge of the spiral arm where star formation was being induced by like compression of that spiral arm. So really, really interesting information that you can get from like IFU observations of hosts and really digging down into the kinematics of what's going on in the galaxies. And we can continue to get really specific about the locations of FRBs relative to star forming regions. I'm showing an image from Marcotte et al. 2020, but also there is really wonderful HST data and further analysis in Tindalkar et al. 2021, looking at FRB 180916. I love this galaxy so much. I love the images, they're so pretty. But looking at this FRB relative to star forming regions in this host, and they're able to get, because of this really, really precise localization and also really great high resolution imaging, they're able to make very precise measurements of where this FRB is relative to these bright star forming regions. How much did it, drift? What does that say about the age of the progenitor and everything like that? And then on the other side is a plot or a figure from Aaron et al. 2016, where they look at and measure the drift of different types of supernovae from the kind of peak brightness in the spiral arms. So assuming that those peaks in brightness are, where the most star formation is occurring, looking at the relative drifts of different transients, or in this case, different types of supernovae. And again, what can that say about the masses and ages of the progenitors of these various supernova types? And they found a difference between types 1BC and 2, which then gives hints as to, okay, well, one is more massive than the other, one is older or younger than the other. So I'm very excited to, continue getting high resolution imaging, but also very high precision localizations, because that is what is necessary to do something like this, to kind of map out where FRBs are landing relative to these structures. You can also look at or measure the galactocentric offsets, so how far are FRBs from the centers of their galaxies. We know, for example, that like long duration gamma ray bursts are generally concentrated in the more central regions of their hosts, and that's shown in the orange CDF line. On the x-axis is our host normalized offset. So we're normalizing across different host sizes. So trying to kind of account for the fact that these hosts are likely different sizes. Some are smaller, some are larger, but we want to normalize across those size differences, and then a cumulative distribution of the measurements. So LGRBs are shown in orange. And then we know that short duration gamma ray bursts are usually found in the outskirts of their galaxies. These neutron star binaries that have experienced really large kicks and are now way off in the distance, and that CDF is shown in red. And lucky for us, FRBs are kind of just right in the middle of both of those. But that gray shaded region is the error on this CDF. So we do have some room to move in either direction as our sample size grows and we can make more of these measurements. And then coincidence, with precise localizations, we can more securely associate FRBs to other objects or events or sources of emission. And this is especially important as we move to hundreds and then thousands and maybe more, tens of thousands localizations across the sky. So I'm showing here plots from three different papers. New et al. 2022, which looked at the FRB 190520, and they made a measurement of a persistent radio source associated with the FRB and its host. And then also Ravi et al. 2022, which looks at the host of and also radio emission from the host of FRB 2011-24A. And in Ravi et al. 2022, they were wondering, well, is it a compact source or is it radio emission associated with star formation, for example? And in Dong, in prep from Vic, who is somewhere I can't see, there she is. They're finding then that radio emission is indeed due to obscured star formation in the host of 2011-24A. And so having very precise localizations of FRBs and also high resolution imaging and also high resolution imaging in other wavelengths can make sure that we're associating the FRB properly to, sources of emission like these persistent radio sources. Is it actually extended radio emission? Is it something compact? And how does our FRB fit into that picture? And then also, if there are other transient events that have occurred in that host, we can make sure that the coincidence of the FRB to some other event are not just coincidence and they happen to kind of overlap on the sky, especially as we're detecting more and more FRBs, this seems more likely. So having very clear understanding of where exactly in the host the FRBs are coming from, I think can help to mitigate this. Another important thing is characterizing the light at the FRB location. I think I've already kind of touched on this, and then also looking at the host morphology. And this was a key to studying or solving the long duration gamma ray burst mystery. So I'm showing some images presented in Fruchter et al. 2006, where they look at and compare the hosts of long duration gamma ray bursts and core collapse supernovae. And in long duration gamma ray bursts, they found that they were concentrated in the brightest regions of irregular low metallicity hosts, whereas core collapse supernovae were distributed across different brightness levels of their hosts and were found in massive spiral galaxies. And the high precision localizations and subsequent, HST imaging really helped them to make these differentiations between these two populations. And then eventually we come, to find out that long duration gamma ray bursts are preferentially existing in these low mass, low metallicity hosts and associated with superluminous supernovae. The measure that they use is called fractional flux, and we also implement this, I think, Wenfei Fong implemented this in studies for short duration gamma ray bursts, and we also did this in Mannings et al. 2021 for FRBs and their locations in their hosts. You can do this for, different wavelengths for infrared or near infrared, and also rest frame UV to study the relationship between the FRB and different stellar populations in their hosts, whether you're more focused on general kind of distribution of stellar mass and older stars or regions of star formation with the rest UV. Also with M81, I imagine, maybe this isn't true, but if, we were to detect the FRB like the one that came from the globular cluster outside of M81, but we put it at a farther distance, we would maybe look at the global properties of that host and say, oh, it's spiral, star forming, all of these things, and maybe have the inclination to associate it with a younger stellar population. But because it was so close and we have such a high precision localization for this FRB, we were able to tell that it did indeed come from a globular cluster out in the halo of the host. So I think knowing the offset and specific location of this FRB is very important in getting an understanding of the possible age and masses and, associated characteristics of a possible progenitor for this FRB, which people think, might be a magnetar created from accretion-induced collapse or white dwarf merger or something like this, which is very different, from a magnetar created from a core collapse supernova or something like this. So what did we learn from 1906 to 8B? I know it's been a second since we talked about it. But across all scales, on cosmic scales, we learned lots about, in the example that I gave, DM cosmic, and then maybe a little bit about DM host. On the global host scales, we learned about the stellar population, we modeled star formation history, we learned about its mass and morphology, beautiful spiral arms and spiral structure, and even a bar. And then on the local scales, we learned about the relationship of the burst to various morphological features and other emission in the host, and then the possible age and mass of the progenitor. So hopefully I have contextualized what the local scales mean. And then kind of looking forward to, I guess, techniques of following up FRBs. I think that AO and adaptive optics is a great resource for us to kind of take advantage of and utilize when we need to do this high volume, high precision imaging of FRB host galaxies. So here I'm showing an AO image of FRB 2021-1127I. And then in the middle panel is the GalFit model of the host, so fitting the central and disk components of the host, and then subtracting that off from the image, you get a GalFit residual, which is shown on the right. And here you can really see this like clear bar in the middle. You see nice spiral structure popping out at you, going towards the outskirts of the host and those two arms. And then, you know, imagining that localization to be even smaller, we can start to get a lot of information about the FRB relative to these structures and star formation and stellar mass and all sorts of things. So yes, and that brings me to the end. So thank you. This is a QR code to a link of a ADS library that I made of all of the references here in the paper, as well as some other papers that I think are relevant, but I did not touch on. So thank you.
Thank you, Alexandra, for a great talk. So I know we have a question online. We have questions in the audience. I also have a question. Maybe I'll kick things off. You know, we know that there is now an extragalactic FRB and a globular cluster. Out to what redshift do you think is it feasibly possible to explore FRBs and other globular clusters with OIR follow-up?
That is a good question. I guess I'm thinking about like, I feel like with increased, you know, precision of the localization of even the redshifts like one host, I feel like you could get a good understanding of like how offset it is from the center and things like that. So but I don't know how much of an understanding you could really get of like something beyond, oh, it's out in the halo. And if you could really associate it with a globular cluster specifically, besides just knowing kind of its offset from the center. So I'm not totally sure. Yeah.
Okay, thanks. Other questions? Jason has a question.
Yeah, great talk. Thank you very much. So I get the impression from your talk and also from what Maria was saying yesterday is that if we actually want to really see subpopulations and constrained progenitor models, we're going to need really a lot of localizations, like, you know, galactocentric distance, all of these things, consistent with many possibilities. One thing I didn't hear you say, though, when you were talking about individual sources and studying them in detail, what about ELT? I mean, in the future, we're going to have a telescope that can maybe resolve individual stars. We can really associate, you know, with VLBI at milli-arcsecond levels, both in optical and in radio, these positions. And I really wonder if, like, on the short term, we won't learn more from some relatively nearby, but not super nearby sources that are studied in really gory detail on kind of parsec levels or so. So your thoughts on that, basically?
Yeah, I think that ELT will definitely be a very powerful tool for resolving hosts and, yeah, FRBs in relation to all sorts of morphological features and all this sort of stuff in their hosts. Yeah, And then do you agree that we need like hundreds of thousands to really get down to some population? I think that I do agree. Yeah, yeah.
Can you just repeat the question so that people online hear it?
Oh, sure. Just if I agree that we need samples like hundreds or thousands in order to separate subpopulations and things like this, right? Okay.
Okay, maybe we can take the question online.
Should I open?
Yeah, why don't? Okay.
Oh, you can.
Clancy, I think this is a question from you. Do you want to unmute and ask?
Yes, certainly. So thanks, Alexandra, for the talk. You showed, I forget which slide it was, the offset distributions, radius from the host. The question from me and a follow-up from Amanda Cook was, does any of this include systematics? Because we know that, the gas towards the center of a galaxy adds extra DM, which makes FRBs less detectable for most instruments. And similarly, optically, to identify a host, there's going to be extinction. Are any of those effects included, and do you think they're important?
We do mention it in the paper, but we don't take it into account when creating this plot specifically. It does seem like it could definitely be an effect where FRBs occurring closer to the centers of their galaxies, yes, would be much harder to detect if we detect them at all. So I think that could, definitely affect this distribution here.
Right, thanks.
Okay, other questions? We maybe have time for one more. If not, let's thank Alexandra again for a great talk. Okay, so next we have a discussion panel. Well, it's a section. So this will be led by myself and Navin Sridhar. Navin, are you able to share your slides? I don't have a computer in front of me.
Sure, I can.
Okay, so the way this will work is we'll introduce two questions and we'll kind of sort of kick things off that way. And then we'll break into groups. So we'll have at least two groups, maybe three here in person. And online, we'll have maybe one or two breakout sessions. The idea being that we'll introduce these questions. There'll be at least two of them. We have some others if we have extra time. And we will discuss amongst our groups. We'll elect, say, one person to bring forward the ideas from the group to the full workshop here, and we'll have a discussion in that manner. Let's see, so. All right. Okay.
Can you see my screen right now?
Ziggy's working on it. Hang on. Okay, there we go. Okay. Okay. Do you want to flip to the first question? Okay. So the idea for the discussion is basically to brainstorm what follow-up efforts and things that we can do with localization information that's poised to give us the maximum amount of scientific return and information to the progenitors of FRBs. So let's go to the first question. I'll introduce that. Right, so it's basically, we're poised to enter an era where we'll be localizing hundreds, if not thousands of FRBs with surveys like CHIME FRB and their outriggers, DSA, and so on, EVN. And the question is, how can we use this localization information to get the maximum amount of information about what FRBs may actually be, what sorts of astrophysical sources may be producing them? So we heard from Alexandra, who gave a great talk about how we can do host galaxy studies, zoom in on the local environments of FRBs, comparing the galaxy nature of repeating and non-repeating FRBs, comparing the properties of hosts to other types of transients like core collapse supernovae and the galaxies where they originate from. We've also heard talks yesterday and also today involving potential links with persistent radio sources and FRBs. And interestingly, two of the hosts are where those persistent radio sources are found or dwarf galaxies. So question becomes, is that significant? Is that just a fluke? How can we explore that with more localizations? And of course, if we've now have very precise localizations from experiments like the EVN and long baseline VLBI, where we've pinpointed repeaters to host galaxies and zoomed in on their local environments. And if you look at if you zoom in with HST and look at the closest knot of star formation, there's an offset. So if you invoke this hypothesis that FRBs are primarily formed from a magnetar channel, it's difficult to explain young magnetar as the progenitor given the offset from the star formation. So the question becomes then, how do we combine or use the localization information that we're about to get from existing or upcoming experiments to sort of answer the question, what are FRBs, what creates them, and get more information? So that's the first question. Navin, do you want to introduce the second question?
Yeah, sure. So the second question is on the efforts that can be put to disentangle the burst features that are arising from intrinsic emission mechanisms versus propagation effects. So we now have a bunch of localized repeaters, and what specific follow-up observations need to be made, and how simulations and other numerical efforts can play a role in disentangling these two effects, basically. Here are 4 examples. One is the variable polarization properties. If there's a temporal variability that's associated with the source, for example, Benyamini et al. Show that it does not depolarize the circular component, whereas if the variability is due to a plasma screen somewhere far away from the source, the temporal screens, the variability while the FRB propagates through it, can cause certain changes in the circular polarization, and so on. Another example is the millisecond timescale polarization angle swings that is seen from, for example, 301A. And another question is whether these sub-millisecond duration temporal fluctuations that are seen from some sources, whether they are, and the amplitude of these fluctuations, whether these are solely intrinsic or they can also be caused due to propagation effects. For example, recently there have been a series of works by Emanuele Sabaki, Ghosh, Iwamoto et al., both analytical as well as kinetic plasma simulations that show the formation of so-called filamentation instabilities in the plasma caused by the propagating FRB, which is a kind of self-modulation, which can cause certain temporal sub-millisecond fluctuations in FRBs. So how can we disentangle these features, these due to propagation from intrinsic features, and how can follow-up efforts help with this? Yeah, so these are the 2 major questions that we have for discussion, and these questions are posted on Slack. And if you want to take a look at a couple of bonus questions, go to D2S1 channel, and there are a few bonus questions too. Aaron, do you want to take over?
Sure. Yeah, so as Navin said, what we're going to do now is we're going to break up into groups. If you need to look at these questions just as a reminder or use them to sort of jog the discussion, they are available on Slack, so you can view them there. So maybe the SOC can help us break up into groups now. And okay, so we're going to start coming together now. We have people from online and also from the breakout session by the coffee. They've probably been enjoying themselves very much. Okay, so I think most people are back now. So why don't we have the groups online summarize their discussion first? Does Navin, do you have a preference or some way to nominate a speaker from each?
Can we have Yosha from breakout room 2 to just share a few words on what they discussed? Thanks.
Yes, sure. So we were a very small breakout room of only 2 people, but we had some nice discussion. So on the first question, I think our credo was that these nearby and very well localized FRBs are very valuable. That's what we, I think, learned in the last days, especially from the talks about supernova and what we can learn from GRBs that really the localization within the galaxy is really what can tell us the most, and well, probably with the smallest biases and so on. Yeah, there were many examples of FRBs on that already. So, and about the second question, we kind of brainstormed a bit, but I don't think we had really any convincing ideas, I would say. Like maybe we can learn something from X-ray about set constraints for some model on when we cannot see X-rays, or maybe can set constraints on the size of the systems from X-rays. But yeah, like I said, I think we didn't have any convincing ideas yet.
Okay.
Thanks, Yosha. Should we?
Yeah, why don't we
have
move to the
Clancy
second breakout session?
Yeah, Clancy from breakout room 1. Can you share a few words?
Yeah, certainly. So we had probably about 15 people in our breakout session, so we didn't get an even distribution at all. We had quite a good discussion on the first point. I think we all agreed that simply identifying the host galaxy might be useful, but that really precisely localizing an FRB and doing very detailed optical follow-up within that host to really understand the exact environment around the FRB is super important. So the example, we have was of 180916, repeater 2, the first repeater localized by Chime to this spiral galaxy at about 150 megaparsecs. And the value of the Hubble Space Telescope in really identifying the kiloparsec offset between the repeating FRB and the region of star formation. So I think we discussed the case also that it's difficult to see globular clusters out to any large distance. And so I think seeing closer, following up closer FRBs, getting really VLBI style localizations, and in particular, trying to get VLBI localizations for apparently once-off FRBs, because now we're limited to strong repeaters now. So I think that briefly summarizes our discussion for question 1. We had a shorter discussion in question 2. It was pointed out that because there's lots of FRBs doing lots of different things, that doing large population studies and building up statistics on, what the on polarization behavior, for instance, is very valuable. So just getting good polarization measurements for many FRBs would be great. And it was pointed out that the European VLBI network gives you full polarization there. I'll also add that ASCAP is a great polarization instrument. It was then also noted that a lot of the propagation effects are not so bad at high frequencies. So getting very broadband, and in particular going up to high frequency observations, where I think high frequencies for us was of order 5 gigahertz-ish, would be incredibly useful. So I think that's where we leave, although I'm going to go ahead and put Jane on the spot for hinting at something interesting coming up in the next few weeks on that. So if you can try to get her to whisper in your ear what that's all about, please do.
Jane, can you unmute yourself?
Yes.
I don't think she wants to talk about it, but I'm putting her on the spot.
Thanks, Clancy. Yeah, so just watch this space in the next few days. We did observe something quite interesting in the magnetic field of a repeat FRB with the broadband system of Parkes. So it will be out in Science in the next few weeks. So just, yeah, keep your eyes peeled on that one.
Perfect. Thanks, Jane. That's all I had to say.
Thank you, Yosha. Thank you, Clancy. Thank you, Jane.
Yeah, well, we're looking forward to that result in Science. So let's see, let's go around the breakout sessions here in person. Should we?
We'll start with Alexa. She's got a mic.
Okay.
Just to quickly introduce myself, I'm Alexa Gordon. So we mostly focused on the first question, And thinking about that, we're tending to see FRBs in star-forming galaxies. How do we go after measuring that? So thinking about using IFUs with adaptive optics, H-alpha filters, ALMA, just really how can we probe star formation of the hosts? I've also thought a bit about the selection effects of going after only the closest or the furthest hosts, what that could be biasing our knowledge of these systems, and then also a bit about the very low redshift FRBs that we seem to be missing for whatever reasons. And again, kind of the biases of what we might be taking away from the host populations by missing these ones.
Okay, great. Should we switch to the next group?
Great. Okay, Alice Curtin. Yeah, so starting with the first question, we talked a little bit about starting to use this redshift information to associate FRBs with other counterparts such as GRBs and supernova remnants. And if we could do follow-up of some of these short GRBs, for example, and get redshifts for all of them, because there's a decent number of short GRBs without redshifts, then we could start to make more conclusive associations possibly between these different classes of objects.
Yeah, hi, I'm Ketan. I'm a PhD student at McGill. Then we talked about like it's better to have an all sky sample of like FRBs, say at a distance of 100 megaparsec. That will help us do a lot of good follow-up observations with a large number of sources. But so like it was brought up, like, for example, if you follow FRB that was discovered by fast and blind search, that will have probably a super high redshift and you would require time on like HST or something to go look for it. So it's better to make a sample of FRBs, nearby FRBs, to do that. And then it was also pointed out that we can make like a subsample of like good FRBs to like just follow up. For example, periodic FRBs, that's a pretty interesting case. So if we find more periodic FRBs in the large samples that we detect, it will be nice to go and look at their host galaxies and their locations and like whether they have something in common and what we can learn from them. And coming to like really zooming in, it'll be nice to have ELT as a facility to look at globular clusters. If like there are more FRBs in globular clusters, then we can use ELT for that. And another point that was brought up was that we can use ALMA as well to do like molecular gas analysis in the local universe and like look at the FRBs localized pretty close and look at the molecular gas distribution, which can tell us a lot about the progenitor system.
Yeah, and then for the second question, for the propagation versus intrinsic effects, we were very broadly saying that maybe follow-up observations and simulations, well, at least follow-up observations might not be the key here. It might be, well, I guess you could say follow-up radio observations of repeaters, so that it would really possibly be repeaters here, which would be able to allow us to distinguish between the two, largely because hopefully we could get raw voltage data for these repeaters and then really start to use simulations to break down the different effects that we're seeing. So for example, use simulations to map like plasma lensing to look at that type of propagation effect and try to distinguish that from more intrinsic emission mechanisms.
And I would just like to add one thing to the first point that it was also added that we should not focus like everything on the repeaters. We should make sure that we do follow up of one of FRBs as well, because earlier we have seen like in the like supernova follow-up observations that if we try and restrict ourselves to like certain subpopulation or like just converge and collapse them into one, we might not be able to learn a lot of things. So it's better to have equal amount of follow-up time, both for one-off as well as repeating FRBs.
Okay, great. Is that everyone or do we have one more group?
Hello, Vishwangi Shah. So for the first question, we discussed that as we get these hundreds or thousands of localizations, it's very important to look at the host environments of FRBs, their host galaxies and burst properties, and to classify them into multiple classes. Like right now, we are just classifying them as repeaters and non-repeaters, but probably there are more classes than that. And it's very essential to do that. Otherwise, if we try to study them all as a whole, it would be a mess. So make more classifications and compare those classes to classes of other transients. For the second question, we discussed that probably it would be ideal to target low DM FRBs because better SNR and also easier to follow up. But we should probably also hold this fact in mind that whatever low DM FRBs we have got till now, like the M81 repeater and the SGR 1935 bursts, they have been less luminous. So if they were probably more farther away, we would probably not have detected them. So maybe they're a different population, but it would be great to study them. And also a very interesting discussion we had about that is that why haven't we detected more low DM FRBs? Maybe because we are misclassifying them as RFI. So that's something to think about.
Okay, great. Let's see, should we open it up in case anybody wants to offer any comments before we go to break, or? Let's discuss over break. Everyone wants coffee and snacks. So thank you, everyone. Let's give our speakers again a round of applause.
Just a quick reminder that these questions are also posted on Slack, and there are a couple of other bonus questions too. And please feel free to add your thoughts there too.